Good evening, all. Am I audible? Okay. So, so welcome to the NPTEL course. This study guide in organic retrosynthesis problem solving approach. So, this course, Professor Samik Nanda already made several videos, like 5 lectures in last week. So, I will be discussing some problems within whatever he discussed in last week. So regarding the course, I will discuss some of the problems. So coming to introduction, so I guess he has covered 5 lectures, 5 videos, each of five half an hour. So yeah. So my slides are visible. Okay, thank you. Yeah. So I'll come into basic first. So introduction to organic synthesis. So I guess all of you knows the first synthesized molecule was urea, or it is called as carbamide. So which was synthesized by German chemist Friedrich Holler. And as you all know, so urea has an importance role in physiological chemistry because it is an end product of metabolism of nitrogenous food, and also it is found in urine. So this Bohler experiment of this urea synthesis, so that answer in the era of synthetic organic compounds, and which also lead to the production of dyes, dynamite, plastics, sulfur drugs, and synthetic fibers, and also the process of petroleum cracking. So this sort of synthesis is very much important nowadays because I will go to the next slide. As you can see, Professor R.B. Woodward. So he's an American chemist from Harvard, and also he won Nobel Prize in 1965. And as you can see, he got a Nobel Prize because of this art of organic synthesis. So he and his co-workers has synthesized many natural products or unnatural products having biological activities. Yeah. So as you can see, this quinine is an anti-malarial drug, and he Professor Rabe Kindler has synthesized this quinine, although he has published a partial synthesis of this quinine. And in 1944, later at 1944, Professor R.P. Woodward group, they have synthesized the quinine molecule, and this quinine in early 19th century, it has an huge societal impact because of this antimalarial activity. Also, he has synthesized this cholesterol in 1951. So cholesterol, all of you know, it helps to make cell membrane, and also vitamin D synthesis. Also, it can make tissues. So now this cholesterol, I guess Professor Somik Nando, in his lectures too, he has uh, he has he has talked about this cholesterol because he has one of the slide he has shown that previously the structure of cholesterol was wrong. So if you see this cholesterol, so this is basically, six linearly fused, and this 6 6 is angular fuse, and this is 6 5. So previously it was not like this 6 6, it was different fashion, 6 6 6 linear fashion. Now after this synthesis of this cholesterol by Professor RB Woodward, so they have shown the correct structure of this cholesterol. So that is why the organic synthesis has an important role in today's life. So also the structure of this cortisone. So this 1951 he has synthesized this cortisone in 1951, which is an steroid hormone. Yeah. So if you see the structures of all of these compounds, so basically these are having many chiral centers, also some complexity in the molecules. So being a chemist, you have to know how you can synthesize on particular molecule. So if you have one chiral center, so there is possibility of two enantiomers. So more the chiral centers, more the complexity. So you have to have one good synthetic methodology so that you can synthesize any given molecule, target molecule, uh, exclusively. Okay. So Professor RB Woodward, now coming to this EJ Core. So EJ Core also an famous American chemist. So he also from Harvard. So also he won the Nobel Prize in 1990 because of his contribution to the theory and methods of organic synthesis. So he is a famous organic chemist. So as you see the molecules, so many more natural products or unnatural products he has synthesized. And this, if you see this molecule longipholin, okay, so it is in bicyclic compound and having antioxidant property. Okay, so in 1957 he has synthesized this longipholin. Also this prostaglandins. Okay, so there are many molecules of this prostaglandin series. So he has synthesized most of the prostaglandin series, and this is the structure of prostaglandin E. Okay, this is in five member ring. This pentanone, cyclopentanone, having two olefin. If you see the molecule, if having two olefin double bond, one is this cis olefin and this is trans olefin. Okay, and also having this carboxylic acid side chain, and this is having this secondary alcohol. So synthesis of this molecule is really challenging, and he has synthesized this. He has published the synthesis of this prostaglandin E2 in 1969. So and you can see what is the biological activity in this. So it can regulate mainly many bodily processes. Also if you see this molecule, so this is another molecule called epidocolin. And yeah, coming back. Yeah, so this FED choline, so it is an antibiotic molecule. Okay, so if you see, this is also having the steroid-like skeleton, not exactly. So it is having this 6 6 bicyclic skeleton along with this 6 5 fuse. This is also an bicyclic mm, uh, skeleton. Okay, 6 5. So this 5 is fused with this 6 member ring. Now if you see this molecule, so it is having this tertiary methyl group, also having this beta. So this alpha hydroxy here, also primary alpha CH2OH. So this molecule also to synthesis this molecule is not a uh, easy job. Okay, so and in 19th century basically they were not having NMR or mass spectrometry or XRD. Okay, so it is really challenging for them in early 90s 80s century uh, to synthesis this complex natural product is heavily challenging, and they have synthesized this molecule with correct stereoisomer. It's really appreciable. Okay, so that is why there so Professor EJ Kore is a big name in organic synthesis, and he got his Nobel Prize in 1990. Also this biotin, if you see biotin also known as the vitamin B7, is the energy source. So if you see, this is a 5 fuse ring, also having this carboxylic acid side chain. Okay, this carboxylic acid side chain, and this 5 it is cis fuse because this both hydrogens are cis. So this synthesis also he done at 1988. So 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 you can see how in early 90s they have Professor EJ Kore or RB Woodward, how they have synthesized highly challenging molecule in those days. Now it becomes more easy because of more experimental facilities like NMR, mass spectrometry. So now coming to what is this ideal synthesis or what is total synthesis. Okay, so basically, yeah. Yeah. So this ideal synthesis, see, as you can see, this title of this slide is ideal synthesis. Now, so this, if you see this puzzle, okay, this graphics. So if you want to synthesize this molecule, so you can see this is how like it is highly complex molecule having many this functional group, also with correct digestereochemistry to synthesize this molecule is highly challenging. Now if you target like if you took any starting material, easily available starting material, and you want to do some methodologies to get your target this natural product, right? Now there is many challenge. So if you see this puzzle, like suppose one chemist, he has chosen this pathway. Okay, first he has taken the starting material and he has chosen the pathway, and he now this coming towards this part. Okay, now he's coming. Now this is the dead end of this part. Okay, because after that the chemistry is not working. Okay, whatever he designed or whatever he planned for his retrosynthetic plan, it is not working practically in this step. Okay, certain step. So what he should do now, so he has to go back the way, and again he has to plan other different part. So like now he has chosen this part. Okay, now he's going to this part, again he is coming to this dead end. Okay, so that is uh, whatever he has planned the retrosynthesis, it is not working after several step. Okay, so again he is coming back and he has chosen this path. Okay, now you can see here is coming, and now it is a dead end for this step. So to find a particular part, like it should work. Okay, any methodology he will think that should work, and that should give the complex this natural product whatever he planned for in his retrosynthesis, that should be um, work. Okay, now so in total synthesis you will get many difficulties by choosing the different retrosynthetic plan, So you have to work properly. Yeah. So you have to plan properly so that you can get the correct retrocentric part, and you can get into the natural products. So you can see, so this part is feasible for his total synthesis. Now, so this is very challenging. Total synthesis is not a easy job. So uh, you have to you have to have many retrosynthetic plan. Among them, few will work, few will not work. And if any retrosynthetic plan is not working, that is not your fault. That is some experimental lack of experimental skill, or maybe this chemistry after certain stage is not working. Okay, so that is why you have to do organic synthesis, and you can explore more of the reaction, and you can easily get into the natural product whatever you have targeted in this total synthesis. Now, what is ideal synthesis? So ideal synthesis is that you have to choose a particular path where you will get less number of difficulties. Okay, so ideal synthesis, this term is invented by Professor Henrikson, and in his paper, this Jack's paper in 1975, he has given a brief idea about this ideal synthesis. Now, if you see, uh, so this is what is ideal synthesis basically. So it should be environmentally acceptable. That means you have to avoid the problematic waste. So after any reaction, any organic reactions, so you will have some waste, okay, or side product or byproduct. Okay, like suppose Wittig reaction. Okay, if you do Wittig reaction with Wittig ylide and any carbonyl group, so after reaction you will get the target olefin and also the side product, that is called pph3 oxide. Okay, in any Wittig reaction you will get this pph3 oxide. So this is waste for so pph3 oxide is the byproduct or side product, but also you can say it is a waste for this organic synthesis, organic reaction. Now you have to, so in any reaction you have to think about a suitable pathway so that you can get uh, less number of waste or less problematic waste. Okay, that waste should not be uh, explosive, it should be neutral kind of things, and it should not be more. Okay, so that's why it is called greenest route. Also you have to avoid some toxic intermediates. Okay, toxic intermediates means you have to, so you should not use any toxic metals. Like suppose if you heard about mercuration, oxymercuration, demercuration, so in the hydration of olefin, so mercury you have to use. So mercury is, it is a toxic element, toxic metal. So you have to use you have to use the reagents in such a way that so it should not involve any toxic intermediates. Okay, so that is called healthiest route. Also, economically acceptable mean, what is that? So this should be cheapest route. Whatever starting material you have selected or targeted, it should be economically cheap. Okay, so the cost of material should be lower. Also novelty, so whatever methodology you have published or you are working, it should be novel. Okay, then only people will appreciate your work. So that is how it is economically acceptable. It should be environmentally acceptable. Now it should be safe and robust. Okay, what does it mean? Safe mean you have to avoid some procedures which, like some risky procedure you should not utilize. Okay, suppose you are using alkali lithium, okay, suppose n-butyl lithium, or secondary butyl lithium or tertiary butyl lithium in your chemistry, okay. But sub if but you have to know, like you can't use those type of alkali lithium in water, okay, because it will be explosive in water, okay. So some risky procedures you have to avoid. And also whatever methodology you have developed in your synthesis, so that should be easily scale up. Scale up mean, suppose you have done the reaction at 10 mg scale or 50 mg scale or maximum 100 mg scale for methodology purpose, but it should work at gram scale also, okay. Otherwise that chemistry is not that much feasible, or I can say it is not robust. So that it should be whatever methodology you have developed, you have to think about that it should be easily scalable, okay. And also sometimes reproducibility factors came, like some group have published some methodology, suppose any methodology reaction, okay, organic reactions. Now in their lab it's working, suppose we are doing the same reaction in our lab, it's not working. So it like that it should not happen, okay. So you have to be careful while publishing your results, or while you are doing the organic synthesis. You have to be careful, and you have to take care of this scalability and also reproducibility factor, okay. So the chemistry should be reproducible, um, also highly efficient, okay. So efficient mean it should be simpler, also it should result in high yield, and it should you can complete with few steps, okay. So that is how one can imagine about this ideal synthesis. And so I guess you got some idea about this ideal synthesis. So now coming to this next slide, where we'll come into the detail of this retrosynthetic analysis. Okay, so Professor Samik Nanda, he has discussed about this the introduction of this retrosynthetic analysis, like what is target molecule, or TGT, or FG functional group, in interconversion, or I can say I will write some of those. Yeah. So just a second. Yeah. So in this slide, so this is so if you see the heading of this slide, retrosynthesis for 2-methyl pentan 2 all. Okay. So this 2-methyl pentan 2 all, if you see the IUPAC nomenclature, so this is one, two, three, four, five. Okay. So now if you see this molecule, so here we will do the retrosynthetic analysis for this. This is a simple molecule. So this molecule is having one tertiary alcohol. So in this center, this is 3 degree tertiary alcohol. Okay. So now in this tertiary alcohol, if you see how we can how we can plan a good retrosynthesis for this molecule. Okay. So if you see this molecule closely, so you can think about uh, this CC bond disconnection or this CC bond. So this is methyl. This is also methyl. So this is symmetrical. Both you can think about this CC bond disconnection or this CC bond disconnection. Okay. Now, yeah. Now, if you think about this CC bond disconnection, right? So what you can think about the starting materials now. So this CC mean, so this so it is having COH bond. Okay, so so you can think about this part may come from acetone. Okay, so like if this CC bond disconnection approach you think, so you can think about these two starting material, right? So this is acetone and this is methyl. uh, so this is the 1 2 3. So this is the Grignard reagent. So you can think about this 1 2 addition of this Grignard reagent into this carbonyl. Okay, now, so this will, so this CC bond, the left side CC bond disconnection approach leads to the two fragments. So one of this is a Grignard reagent and this is the acetone. Okay, so if you add this Grignard reagent into this acetone, you will get the your desired starting your desired compound. Okay, that alcohol. Now how you can prepare this Grignard reagent? Okay, so you have to take the corresponding this propyl bromide. So and if you treat this propyl bromide with this magnesium zero. Okay, magnesium zero, so that mean you have to prepare this Grignard reagent in situ. So you have to take this propyl bromide and magnesium turnings. Okay, so magnesium turnings, and if you mix at any etherate solvent like THF or diethyl ether, you can easily get this Grignard reagent. Okay, now after preparation of this Grignard reagent, what you have to do, you have to add this Grignard reagent into this acetone. Okay, and you will get the desired compound. Now, so in so so in this retrosynthetic plan, we have talked about this CC bond disconnection approach. So we can think the other CC bond disconnection approach. How is that? So this CC bond disconnection approach. So what it will give? So this CC bond disconnection, right side CC bond disconnection approach gives these two starting material. One is this methyl magnesium bromide and another is this ketone. Okay, now similarly, okay, so this Grignard reagent you can prepare from methyl bromide or methyl iodide. Okay, so if you take methyl iodide, then you will get corresponding methyl magnesium iodide. Okay, now so how you'll prepare? Similarly, you have to take this magnesium turnings. Okay, magnesium zero pieces, so you can get from magnesium turnings, and if you mix this magnesium and methyl bromide in diethyl ether, you will easily get this methyl yeah. Yeah, if you see, if you think the reactivity, methyl iodide is more reactive, so you will easily get like the time. So you will get both Grignard for methyl bromide as well as methyl iodide, but for methyl iodide you will get like very fast. So that is the difference. Okay. Yeah. So yeah, so this Grignard reagent you have prepared, and how you can prepare this ketone? So you can prepare this ketone from this olefin. So 1 2 3 4 5. This is propene. If you do this oxymercuration demercuration, you can get this that silver chemistry UAG OAC, this silver chemistry. If you perform, you will get this first you will get this secondary alcohol, and then you have to next step you have to get the oxidation. You have to do the oxidation of secondary alcohol to get this ketone. Okay, so that is how. So you can plan So you can have many plans for any desired molecule. Okay, so if your target is more complex, that time you will have more different retrosynthetic plans. Okay, so here in this case both retrosynthetic plan will easily work because both are simple. Now this retrosynthetic uh, so so this is called retrosynthetic trees. Okay, so I guess Professor Samik Nando has introduced this term, uh, this retrosynthetic tree. So where you can see it is like looking like tree, so both left hand side and right hand side you can by retrosynthetic analysis you can get into the easily available starting material. So that is how you have to look into the materials. Now next slide. Yeah, so this is one of the retrosynthetic analysis approach. So based on Diel-Sundar approach. Okay, so so this molecule, if you see this molecule, what it is having? It is having basically a six-member ring. Okay, and also having this methyl ester methyl ester both side. Methyl ester, if you see the stereochemistry, that is trans. Okay, both methyl ester is trans. Now what you have to think about this molecule while planning? So basically if you see any six member ring, so ideally you should think about Diel-Sundar reaction. Okay, 4 plus 2 cycloaddition reaction where you can easily get a six member ring. Okay, so depending upon your target molecule, if you can get if you can get many six member rings from Diel-Sundar reaction, or sometime it is not possible to get uh, for other case. So you have to think for that, you have to think about some other synthetic plan. So now in this molecule you can get easily from Diel-Sundar reaction. Suppose in first step, if you see, so this is basically reduction of if in the first retrosynthetic plan, so this is the reduction of this double bond. Okay, so and you can get this your target molecule. So reduction, so that can we can call it is functional group interconversion. Okay, so basically reduction of this double bond. Okay, now if you and so this is now cyclohexene type of intermediate. Okay, cyclohexene mean you can easily get from Diel-Sundar reaction by doing this, by taking this cyclobutadiene, butadiene and this dienophile. Okay, so we have to take proper dienophile because in your product, in your Diel-Sundar product, so if you see the stereochemistry of this methyl ester, that is trans, so you have to take this trans olefin for this for choosing this dienophile. Now if you want to discuss this stereochemistry, how stereochemistry comes, so basically you have to draw this diene. Now suppose diene is in top phase. Okay, so it is top phase and dienophile is coming from bottom phase. So this is the ester CO2R and this is Me, and this is ester. Yeah, so this CC1 is forming and this CC1 is forming. Okay, so if you see the stereochemistry, so this will go down. So it is, if it is coming from, if dienophile is coming from bottom phase, so this ester will go down and this methyl and this ester will go beta. So this stereochemistry will be beta. Okay, and this stereochemistry will be alpha. So accordingly you will get the desired stereoisomer. Okay, so now this is not the racemic sorry enantioselective selective Diel-Sundar reaction, so you will get both isomer, both racemic, both racemic product you will get. So that racemic product mean, so from top phase also dienophile can come, or and bottom phase diene also can come. So for that purpose you will get the completely opposite isomer of this product. Okay, So as it is not racemic, so this will be endo. Yeah. So yeah. So in this molecule, so you have this six member ring, so you can get easily it form this via this Diel cellular reaction. So you can plan for Diel cellular reaction to get any six member ring. Okay. And what you have to do after Diel cellular reaction, you will have this cyclohexene. So later you have to reduce this H2 palladium carbon. You can reduce in hydrogen palladium carbon condition. Okay. So that is not a difficult job. So now in next retrosynthetic plan, so yeah, so if you see this molecule, yeah, this molecule, if you see this, so first this is 1 4, this is 1 2 3 4 1 4 diketone compound. Okay, so this is 1 and 4, 1 4 diketone compound. So how you can plan? So basically, the NAP reaction here we have plan. Okay, so this carbonyl you can get from NAP reaction. Okay, so if you treat with titanium trichloride, so there are many more conditions. Okay, or you can take dbu dbu and reflux. Okay, if you do, you will get the NAP reaction product, so basically nitro to carbonyl. Okay, so if you, so in the first step we were thinking about this NAP reaction to get this carbonyl group from this nitro compound. Now this is very easy now. So if you have if we disconnect this CC bond, okay, so that means if we take this methyl vinyl ketone, yeah, and this nitro compound, okay, so and if we treat with base, okay, suppose triethylamine, any weak base also it will work. Okay, so if we take, or dbu also it will work. Okay, dbu also it will work. Yeah, just a minute. Yeah, so if you treat this compound nitro derivative with any base, and you can do this Michael addition reaction. Okay, so Michael addition mean you have to generate one carboanion, and you have to add this in any alpha beta unsaturated carbonyl compound. Okay, so this is now methyl vinyl ketone. If you add this reaction, so if you add this nitro derivative carbanion to this methyl vinyl ketone MVK. So this is MVK. So you will get this Michael addition product. Okay. Now next step you can do this is mm, uh, uh, the NAP reaction. Now if we don't want to use NAP reaction, there is another plan how we can get. Okay. So basically we have to get yeah, we have to break this CC one. So now in this retrosynthetic plan how we can get, so this is the methyl vinyl ketone, and also we have to take another this this acyl intermediate. Okay, this yeah, if we delta so if we add this carbanion, okay, into 1 4 addition fashion, you will get this 1 4 the product. How we can get this, like this is the synthetic synthon, and the synthetic equivalent should be like this pH. So if you have 1 3 diethine, okay, so basically diethine chemistry. So this is the 1,3 diethyne. So this proton, okay, so this proton is highly acidic because of this sulfur. So if you treat this proton with any butyl lithium, n-butyl lithium, okay, let's say n-butyl lithium. So n-butyl lithium is base, so it will abstract this proton, okay. So this will abstract this proton and it will generate this carbanion, okay. Now you can add this carbanion to this methylvinyl ketone to get this product, and at the end you will have this diethyne, and you have to cleave this diethyne by silver, okay, Hg2 plus, okay. So that is how also you can get this product, this one for diketone compound. So you can see there are many methods to get any desired product. Now coming to the next retrosynthetic analysis, okay, so this is another interesting example. Yeah, so if you just see this molecule, so this is having this 6 5 fuse ring with trans geometry, okay. So the ring junction is trans. Now how you can get this trans fuse 6 5 ring, okay. So if you do the functional group interconversion, so basically you can get this amine from this aldehyde via reductive amination, okay. If you treat this uh, compound with aldehyde with amine, you will get this, and then reduction you will get this amine, okay. Now this aldehyde intermediate, how we can get? So if you see, so this CC1 disconnection approach leads to this compound, okay. Now what is this reaction? So this is an cyclization reaction. So this, if you see, one cycle is formed, okay. This is called cyclization, okay. Konya in cyclization reaction, okay. So this Konya in cyclization reaction can be done under thermal condition, or any in the presence of Lewis acid like silver triplet or any gold catalyst. So this cyclization can possible basically. So if you think about, so this is aldehyde, right? So if you think about enolate, okay, so aldehyde can be in so aldehyde can have the tautomer of this enol, okay, enol. So that enol can attack to this olefin, so this double one, and it will give this 5 member ring, okay. Now I will discuss in this in the next slide how it is happening. So and this intermediate, so this Konya in precursor, so this is basically Konya in reaction precursor, okay. So how you can get? So we can easily get from this 1,4 addition of this homoallyl grignard. So this is homoallyl grignard, right? And this is the unsaturated aldehyde. So if you do the Michael addition reaction like last slide, so 1,4 addition, if you do 1,4 addition, if you do, you can get this Konya in cyclism precursor. So you can and this grignard you can prepare from the bromo derivative. Now in next slide, yeah. So in next slide, how this Konya in reaction is happening, you can easily see. So this basically this is having this aldehyde and this double bond. Triple bond, if it is having triple bond, it will also work, okay. So if you provide this molecule heat or Lewis acid basically silver or gold base Lewis acid you have to use, okay. Now, so or if you heat the reaction more than 200 or 300, around 200 or 300 degrees centigrade, you will get the desired conversion, okay. So so basically, so it will be in equilibrium with this tautomer, okay. So this is aldehyde and this is enol, okay. Now if you see the electron pushing arrow, so this OH bond will break and this enolate will attack to this olefin, and you can easily get this 5 member ring, okay. So this is basically enolization followed by on 5 hydrogen shift, on 5 hydrogen shift. So basically this hydrogen is coming to this carbon, okay. So if you count, oh, this is 1 2 3 4 5, okay. So this is, that is why this is, so this arrow basically it is taking this hydrogen. So this is one number and this is five number carbon. Okay, so this is why it is called uh, 1,5 hydrogen shift. Okay, so Konyan reaction is very useful in organic synthesis because you will get cycle. Okay, so depending upon, so if you have this three carbon chain here. Okay, suppose you are having this two carbon chain. If you are having three carbon chain, you will get the corresponding six membering here. Okay, in product you will get six membering. So you can, according to your convenient, you can use this Konya in reaction in order to get the ring product. Okay, so, and okay, this Konya and this Konya precursor, how you can get. So basically you have to take this alpha beta unsaturated aldehyde and this homoallyl grignard. Okay, this how you can prepare. You can prepare from this one two three four, yeah, this bromide. Okay, this homoallyl bromide, if you treat with magnesium, you will get this homoallyl grignard. Okay, and if you do the 1,4 addition, you will get this coniine precursor, and then you will get this cyclized product. Now how you will get this amine? So there are many methods. Suppose you have taken, um, suppose, so this is the aldehyde, right? If you treat with benzylamine mean BnNH2. Okay, so benzylamine, so you will get this NH BN. Okay, so you have to use benzylamine followed by sodium borohydride. Okay, so imine, first imine will form, then the reduction of this imine by using sodium borohydride, you will get this NHBN. Okay, now this NHBN you can easily deprotect this. So this is the secondary amine, and you can easily deprotect any benzyl group like this uh, OBN or NHBN by treating with hydrogen palladium carbon. Okay, so basically reduction will happen and you will get the free amine. Okay, NH2. So this is how you can get this your desired target, the targeted product molecule. So coming to next slide, which one? This Grignard addition. Okay, so this aldehyde, right? So first aldehyde, if you treat with benzylamine, so this is just primary amine. So first you will get the imine. Uh, Suppose this is R. So first you will get NH NHBN. Okay. So amination. So imine will form, right? So this benzylamine, it is, so amine will attack onto this aldehyde, and then water elimination, you will get this imine. So then this imine, so this is basically imine. If you reduce this imine by using sodium borohydride, so you will get this single one here. So that is the case. Okay. Hmm. Yeah, you can use, but so basically this concentrated acid, that will be very harsh. So like this, in this substrate, if you see this substrate, this is very simple substrate. Okay, so you can do. But if your substrate is having many aldehyde or acetyl ketal or many functional group which is not acids, which is acid sensitive or base sensitive, so you have to avoid this concentrated acid conditions. Okay, so depending upon your substrate you have to choose the correct reagent. Okay, so you can use here, nothing will happen. But if you have any complex functional group which is acid sensitive, in that case you can't use, right? Okay, so coming to next slide. Yeah, so this is an interesting example. So if you see, sorry, mm, so if you see this molecule is having this. If you consider this is alpha, this is beta, gamma, delta, epsilon. Okay, so this is having delta epsilon alkyne and this carbonyl. Okay, so how you can synthesize this molecule? So this is very interesting example of this Eschen-Moser fragmentation. Okay, so this is Eschen-Moser fragmentation, very known reaction. So how you can get? So this you can get from this epoxy ketone. Okay, so this is basically epoxy ketone. And if you fragment this CC bond, okay, of this parent six member ring, you can get. So this is an fragmentation reaction, Essen-Moser fragmentation. If you disconnect this CC bond, you will get this your desired product. So, and how you can get this epoxide? Basically if you have this alpha beta unsaturated carbonyl, and if you do epoxidation, you will get this epoxide. Okay, now I will ask you, so how we can do epoxidation of this alpha beta unsaturated ketone? Can anybody answer it? No, no. So I have asked because this is having, if you see the functionality na, so MCPBA is electrophilic reagent. Okay, so yeah, yeah. So why we have to use that condition here? Because MCPBA is electrophilic epoxidizing agent. For that, you need some nucleophilic, mean not nucleophilic, electron rich double bond. Okay. Now in this case, this double bond is not electron rich because it is having in conjugation with this carbonyl group. Okay. So this is basically very electron less electron like electrophilic. This double one is electrophilic, so you have to use nucleophilic epoxidizing agent, that is. So you answer now H2O2 NOH. Okay, so that is uh, nucleophilic epoxidizing agent, H2O2 NaOH. Oh, it's minus. Okay, so that will give this epoxide. Okay, so nice. Now after getting this epoxide, how we can convert to this delta epsilon triple bond? Okay, so if you treat this compound with this tosyl hydrazone, okay, so basically tosyl hydrazone, sorry, tosyl hydrazine. Okay, tosyl hydrazine, and if you treat this tosyl hydrazine with this carbonyl group, carbonyl compound, you will get this corresponding tosyl hydrazone. Okay, now this tosyl hydrazone, if you treat with base, okay, so base what will happen? So it is having one proton. Okay, this proton, so base will abstract this, so base will abstract this proton. Now this proton, after abstracting this proton, this will be n minus. So now this minus will fall here, and this nc double bond, so it will, one of the bond will migrate to this cc bond, and this co bond will cleave. Okay, so what basically you will get, basically you will get this intermediate. Okay, now now here this whatever O minus, this will fall here to give this carbonyl, and this CC bond will break and it will give this triple bond, and this CN bond will break and it will give nitrogen. Okay, so this N triple bond N, so that means nitrogen. So here nitrogen gas will release. So this is the driving force of this reaction. And also this tosyl anion. Okay, so in this reaction what is happening, this nitrogen is releasing, so this is the driving force of this reaction. Also you will get this six member CC bond cleavage, and in order and followed by you will get this alpha beta gamma delta epsilon triple bond. Okay, so this is called SN Moser fragmentation. So this is very much important for net, CSR net, as well as GATE related exams. Okay, so you have to be careful by choosing appropriate reagents and appropriate substrate. You can get many fantastic products from simple substrate. Okay, so now coming to the next slide. Yeah, so next slide. So this is now little complex molecule. So whatever we have discussed, those are pretty easy. Now this is some of the complex molecule, not that even that much big complex, but it's okay. So we can synthesize this molecule. How we can plan this molecule? Okay, so if you see this molecule is having this lactone, 5 member lactone. Okay, also having this triple bond, so this is the terminal triple bond, and having this aromatic quinoline side part. Okay, so how we can disconnect? Now I guess all of you heard about coupling reactions. Okay, so we have to utilize coupling reaction, cross coupling reaction here. So how? Basically if we disconnect this CC bond, okay, so this CC bond, what will happen? So this is called Sonogasira coupling reaction. So coupling reaction between this triple bond, so basically this is CH. Okay, CH. So coupling reaction between this is terminal alkyne. Okay, having CH and having this aromatic iodide compound. So basically this is quinoline here. So this is 1 2 3 4 4 iodo 5 6 6 methoxy quinoline compound. Okay, so if you do the Sonogasira coupling reaction between these two fragment, you will get this the coupling product. Okay, so now what about this? So this is commercially available, this quinoline fragment. Now how we can synthesize this molecule? So this is very interesting. So two reactions are involved in this to for synthesis of this molecule. Two main reactions are involved. Like first is yeah. So first, this compound molecule could be synthesized from this vinyl dichloro vinyl derivative. Okay, so this is the target product, target molecule. So by treatment with N-butyl lithium, we can get this triple bond. Okay, so if you heard about Corefus reaction, in Corefus reaction, so they have converted the vinyl chlorine derivative to this triple bond. Okay, you can easily look into the Corefus. Okay, Corefus reaction. Think if you go to the Corefus reaction, so this conversion is known already. Okay, now how you can prepare this compound? So basically very interesting reaction here it is involved. So this is how you can think about this reaction. So this is the sp3 iodide. If it is sp2 iodide, so we can think about coupling reaction. Now sp3 iodide, it is less known. Okay, coupling reaction is less known. So we have to think different approach to synthesis, to coupling these two fragment, okay, this C and this C bond, okay, how we can coupling, how we can do couple, okay. So here we have to utilize radical reaction, okay, radical reaction. So I will discuss in the next slide. Radical reaction we have to discuss, and then how we can get this compound. So basically this compound, if you see, this is 5 member lactone and having iodine here, okay. So this is I guess I am sure Professor Samik Nando, he discussed this iodolactonization or halolactonization in I guess third lecture, okay. Yeah, I guess in the third lecture he has discussed about iodolactonization. Yeah, iodolactonation, okay. So this you can get from iodolactonation. How, we'll see in the next slide, okay. Yeah. So if you are having this 1 minute, if you are having this compound ester derivative, and if you treat with this acid H3O plus, okay, you will get the acid, you will get this corresponding carboxylic acid, okay. Now what you have to do, you have to treat this olefin with iodine, okay. So this mechanism already discussed by Professor Samik Nanda in third or fourth slide, I guess. So if you treat this compound iodine with iodine, so you will get this bridge iodinium ion, okay, bridge iodinium ion here, okay. So olefin will react with iodine to form this bridge iodinium ion, okay. Now, this bridge iodinium ion can be opened up by this carboxylic acid. So, if you treat with sodium bicarbonate, so that will take proton, and this seed carboxylic anion will attack to this carbon, and you will get this open up product. Okay, so basically you will get this product. So this reaction is called, as iodine is involved here. So this is called iodolactonization. Okay, iodolactonization. Okay. Now, this iodine lactonization, after getting this product, this iodine derivative, so what we have to do, we have to install this side chain. Okay, this side chain installation need to be done. How we have, how we can think about this uh, this installation of the side chain? How? So basically, so there is one known reagent. Okay, this is known in radical chemistry. Okay, so in radical chemistry, it is known to install this vinyl dichlorovinyl derivative to any Rx center. Okay, you can treat this compound with peroxide, and in chlorobenzene reflux, if you do, you will get this coupling product. So this mechanism is basically via the coupling radical coupling reaction. How it is happening? So if you draw the, so this is chlorine, this is chlorine. Now this is having SO2, SO2 ET. Now if we think about, this is Ri, okay, this is Ri. So in Ri, eventually in presence of peroxide, it will generate this R dot, okay, this radical. Okay, now this R radical, this R dot, so this radical, it will add to this double bond and it will open up, okay. So now, so this is reversible. Basically you will get chlorine, chlorine, and this radical here, and here now if you see, this R is eventually, it is connected with the carbon, these are carbon, okay. And if you, and you have to remove this SO2 ET. How you can remove? Simple. Basically, this bond will break homolytically, and you will get double one here, chlorine chlorine, and you will get the C desired carbon R bond. Okay, so this is, if you see, this is very interesting example. uh, yeah, this is very interesting example of how radical chemical. Yeah, yeah. So this is a interesting, if you having this Ci bond na, iodinated compound, so in presence of normal sunlight itself, it will give the radical. So for initiating purpose na, you would need, suppose you are having uh, Avogadro number of your Ri. Okay, Avogadro number of Ri, for initiation purpose only one number, one molecule, if it generates R dot and I dot, so that is sufficient to carry out the further reaction. So now eventually this SO2 ET radical is forming na, so now it will carry out to uh, it will help to give this Ri bond. So whatever sunlight, what when you are doing any reaction and you are having dealing with this R iodine compound, okay, iodinated compound, normal sunlight is having important role, like it can take initiation. Okay, so sunlight, in presence of sunlight, the simple one molecule R I homolytic cleavage is sufficient. Okay, so that is how it is happening. Okay, so here you don't need like AIBN kind of stuffs. Got it? Yeah, thank you. So yeah, so after getting this vinyl dichloro derivative, so your next target is to do the formation of this triple bond. Okay, so if you treat this dichloro compound with n-butyl lithium, so basically lithium halogen exchange will happen and it will give this alkyne. So you can get this conversion in Corefus reaction. Okay, now this triple bond, basically if you do the Sonogashira coupling reaction, so Sonogashira coupling reaction, you need to use this palladium to, yeah, palladium 2. This is here, it is palladium 2, right? So palladium 2, and you need copper iodide also, and another base you need triethylamine. So I will show the mechanism of this reaction, Sonogashira coupling. Yeah. So how it is happening? So basically, if you are having this palladium pieces, okay, so palladium 2 pieces, okay, so this is palladium 2 now. Here it is palladium 2, and what will happen first? Oxidative addition of this aryl iodide. Okay, so oxidative addition of this aryl iodide, it will give to this intermediate. Now you are having this alkyne. Okay, so this alkyne we are having, and also we are using this triethylamine as a base. Okay, and this base will abstract this alkyne proton as it is highly acidic. Okay, this is sp proton, right? So sp protons are having are highly acidic, so this can, triethylamine is sufficient to abstract this proton, and it will, and in presence of copper iodide, it will give this intermediate. Okay, and now what will happen? Transmetallation. Basically this copper and alkyne, so this alkyne will move to this palladium from copper. So this is why it is called transmetallation, mean metal, so alkyne is changing his metal partner from copper to palladium. Now this palladium, so this alkyne is coming bounded to this palladium. Now Yeah, now this trans cis isomerization will happen of this ligand exchange, not ligand exchange. This trans cis isomerization of this ligand in palladium center, and now this reductive elimination. So reductive elimination of this palladium center, it will give this Sonogashira coupling product. Okay, and you will get this palladium 2 again. Okay, so this is a catalytic cycle. You can use 10 mole percent of palladium and copper iodide also 10 mole percent. You will get the these are Sonogashira coupling product exclusively. So these reactions are very good uh, in terms of yield, like how efficient. It's very nice. 1 minute. Yeah. So now you can see how. Uh, so in this retrosynthetic analysis, you can see how many reactions are involved. Okay, right? First is the Sonogashira cross coupling reaction. So here it is 1 minute. Mechanism. Oh, okay. What is your name? Sagnik. Okay. Okay, I'll discuss again. So, so you're MSc student or BSc? Okay, nice. So I will explain again. No problem. So basically, in cross coupling reaction, you have to use some palladium two catalyst. Okay, so because 1 minute, just stay away. Yeah. So this palladium, so here this palladium Cl2 pph3 whole 2, right? So this is palladium 2 here, okay? If you check the oxidation number, it is palladium 2. Now this is palladium and ligand is pph3. And now if you do the oxidative addition mean the oxidation number of palladium 2 will now become palladium 4. Okay, so oxidative addition, after oxidative addition, so oxidation number will get increased by number of 2. Okay, so this palladium 2 to palladium 4 along with this oxidative addition with rx. Here rx mean, here it is quinoline, this ci bond. Okay, so this is aromatic. Here basically it is aromatic iodine. Now, so oxidative addition is happening here. So you will get this. This is basically R mean Ar and X mean iodine. Okay. So this is palladium 4. Sorry, not radical. It will not radical actually. It is yeah. So if you in MS, I guess in organometallic chemistry in MSc first sem, you will get more ideas, detailed ideas about how oxidative addition and reductive elimination is happening. Anyway, you just get the idea how it is coupling reaction is happening. So now this after oxidative addition, so this is your intermediate. Now what about this alkyne partner? So we were having this alkyne partner, right? So this alkyne partner, if you remember, this is having CH. Okay, now triethylamine is enough capable of this to abstract this CH proton. Okay, SpCH proton. So it will abstract this proton and it will give this tertiary amine salt. Also copper iodide we have taken here. Okay, so this copper and this C bond will form. Okay, now what will happen? So this alkyne, so this alkyne is will move from copper to palladium. Okay, here copper to palladium. Okay, so it will move to so this is called transmetallation. Transmetallation mean like transposition of one metal to another metal. Okay, basically this alkyne is coming from copper metal to palladium metal, so it is called transmetallation. Now so this, if you see this ligand are like trans. Okay, so the cis trans isomerization is happening in situ, and you will get this two fragment close. Okay, so these two fragment is close to each other now. So now reductive elimination, here also it is palladium 4. Okay, here also it is palladium 4. Now reductive elimination, you will get removal of this R and alkyne. R mean basically aryl. So basically C and aryl bond will form here. Okay, so this new CC bond is formed here. And also after reductive elimination, you will get palladium 4 to palladium 2. So you will get the original catalyst. Okay, palladium 4. Now this cycle will continue. So that's why you need palladium catalytic amount. So it is catalytic process. So you got it, I guess. Saknik, did you get? Oh, okay. Yeah. So now coming to next slide. Yeah, this is another interesting example. Why it is interesting? If you see this molecule, it is highly complex. If you think this molecule, how you can think of retrosynthesis? Okay, so it's you can think about Diel cellular reaction. Okay, so this bicyclic compound also can be made via Diel cellular reaction. How? So if you have so this is an bicyclic system. This is two bicyclic system, and along it this CH2 bridge. Okay, so how you can make? So if you think about this molecule, it is having this olefin here. That mean diene should be like this. Okay, so that means diene should be like this, because all after Diel reaction, this olefin, this new double bond can form. Okay, now what is the dienophile? Here dienophile is interesting. What is the dienophile? So basically dienophile, it is having yeah, this carbonyl. So this is the six member ring, right? So this is one, two, three, four, five, six member ring. Now what could be the dienophile? Okay, so dienophile, it is like it is intramolecular dissociation reaction. Okay, so intramolecular dissociation reaction mean dienophile is present in itself in diene with diene. Okay, so how it is? So this is the side chain is having this CH2 olefin. Okay, CH2 and 1 2, and this olefin 1 2, this olefin. Okay, so if you having Diel cellular reaction with this C bond and this C bond, you will get the same complexity. Okay, same complexity, and you are having this OSC. So I guess you can visualize this molecule, how you can get this deals molecule via Diel cellular reaction. Okay, so huh, yeah, this methyl is missing here. I am sorry, this methyl is here. Okay, I have missed one methyl. Now fine, right? So you have this here, this methyl group, right? Yeah. So if you think this complexity, so you can get you can visualize via this approach. So this Diel-Cellular reaction. So Diel-Cellular reaction of this intermediate. So this is diene and this is dienophile. You can get this complex structure. So how? So you can think how one conversion, that is 4 plus 2, can generate complex molecules. Okay, so Okay, that is okay. So now this how we can get this deal cellular dyne. Okay, so if you see, this could be uh, uh, this we could get from this phenol. Okay, and this is one paper, one known so this work, so this is basically de-aromatization. Okay, so de-aromatization is not a easy job, because aromatic compound is highly stable and you are doing de-aromatization of this compound, so that is not easy. This is always difficult stuff. So this Professor Peter Yates, uh, he has so he work on this type of substrates and like dearomatization how to do with phenols, and he has developed this dearomatization strategy. Okay, so lead tetracetate can do dearomatization of this phenol, and you can get this diene. Okay, so how it is happening? So if you see, so in presence of lead tetracetate, you can get this dearomatization product. So one of the acetate will uh, come here. Okay, so after to this alcohol. So basically, this oxygen will coordinate with this alcohol. Oxygen will coordinate with this lead, and uh, in situ this acetate will attack at this carbon. Okay, so and you will get this dearomatization. So if you see this paper, Canadian Journal of Chemistry by Peter Yates, you can get many many works on this dearomatization problems. Okay, so after getting this dearomatized product, so simply if you heat this molecule, you will get. So deal cellular reaction is very nice, because if you don't need any reagent, extra reagent. Okay, so you have to just you have to provide heat, thermally you will get this 4 plus 2 cycle addition, and you will get this complex topology. Okay, so this is how you can get you can utilize deal cellular reaction, follow dearomatization of phenol followed by deal cellular reaction. You can utilize in this synthesis. Okay, retrosynthetic approach. So very interesting example. Now we'll see the last example of this today's discussion. So this is yeah. So if you see this molecule, so this is a seven member ring. Okay, so whenever you have given any target molecule, you have to think like what type of functional group it is having, how many rings is it is having, how many stereo center it is having, what is the ring size of the natural of the targeted product. So like that you have to do visualization. Okay, so it is, if you see this molecule having 2 methyl with cis stereochemistry, also having this 1 4 1 2 3 4 1 4 diketone, and having this 7 member ring. Okay, so how we can get this? So I guess uh, Professor Samignando, he discussed about this D Mayo reaction. Okay, D Mayo reaction in I guess lecture 5. Okay, so lecture 5 video, if you watch carefully, you can get idea about this D Mayo reaction. What is D Mayo reaction? I will explain it again. So basically, D Mayo reaction is 2 plus 2. It is a combination of two reaction. Okay, 2 plus 2 followed by retroallol reaction. Okay, and retroallol reaction. Okay, so this is combination like D Mayo reaction is 2 plus 2 cycle addition followed by retroallol reaction. Okay, so how it is so if you see this molecule, how we can plan via D Mayo reaction. Okay, so this could be synthesized from this bicyclic compound. So this is 5 member and 4 5 4 fuse 6 fuse bicyclic compound, and this how we can get via 2 plus 2. So this is one of the diene, sorry diene of this is one of the olefin, and another olefin you can get via enolization with this OH. Okay, So this in all, okay, you can, if you expose with H nu, you will get this 2 plus 2 cycloaddition product, okay. So in forward synthesis, so this is the retrosynthesis. In forward synthesis, so yeah, forward synthesis, so this arrow it is given mean this is the retrosynthetic arrow, okay. So never get confused with retrosynthetic arrow and forward arrow, okay. So this is retrosynthetic arrow, and this type of arrow is forward arrow, okay. So this arrow will use in forward synthesis, okay. This is forward synthesis. So forward synthesis will use this type of arrow or equilibrium arrow if it is in equilibrium, okay. Now we have to take this diketone 1,3 diketone compound cyclic, this 5-member ketone. So it is in enolized in tautomer, so it should be in equilibrium with its tautomer, so this enol. So now if you do carry out this 2 plus 2 cycloaddition reaction, okay, 2 plus 2 cycloaddition reaction, you will get this cyclobutane ring, okay. So cyclopentane ring is already there. Now you are forming this CC bond, okay. So you will get another butane ring. So this is 5 4 fuse cyclobutane ring along with this alcohol and this carbonyl. Now if you treat this compound with sodium methoxide or any other base, so basically what will happen, so base will abstract proton from this, okay, sorry. So base will abstract proton of this alcohol, and this OH bond will cleave and this bond will fall here, and this CC bond will break, okay. So this CC bond will break and this bond will come here and it will give this enolate, okay. So this enolate will form. So basically you are breaking this CC bond and you will get 7-member ring, okay. So this is called retroallol reaction, okay. So retroallol reaction, so basically it is reversible of allol reaction. So retroallol it is and reversible, it is reversible of allol reaction. So in this allol reaction, sorry, in this retroallol reaction you will get this, you will generate this enolate, right. And if you so this enolate will take proton from solvent methanol and you will get this carbonyl compound, okay. So you can see how easily you got this uh, yeah, so how easily get you get this 7-member ring with this 1,4 diketone and this cis stereochemistry here, okay. So this cis stereochemistry, if it is cis stereochemistry, that means you have to take this cis olefin, okay, cis olefin. So this cis olefin is giving this cis geometry of this 2 methyl. If you take trans trans olefin here, if you have taken trans olefin you will get the trans stereoisomer of this methyl, okay. So that is okay. So according to your target material you have to take you have to think about your desired starting material, and starting material should be cost effective and cheap and economically viable, okay. So you should not think about advanced stage starting material, so that you have to buy in, like that you can't buy, okay. So if you think about easily available starting material, that and that will leads to cost effective synthesis, okay. So that is how we have discussed many retrosynthetic problems of many molecules. Also we have showcased how Professor R.B. Woodward and Professor E.J. Corey, how they got, why they got Nobel Prize, and how they have synthesized many molecules with complexity and with different biological activity, okay. So that is why organic synthesis is highly like it is demanding area of it is one of the demanding area, you can't avoid it, okay. So like I remember one quote by Professor um, EJ Kore. So I guess he talk about organic synthesis. You can't, maybe you can't like, b- or you like you can like or you can hate organic synthesis. You can like or you can hate, but you can't avoid it. Okay, if you avoid it, so the society, whole society will get bad impact, okay, of it. So you have to, if you want to pursue higher studies in organic synthesis, you have to have the basic concepts uh, of this synthesis, and also some name reactions also you have to keep in mind. So, and you can think anytime and you can visualize them. So by that you can improve your knowledge, okay. So that is so by this we'll stop today, and we'll discuss next week some more challenging complex target molecules uh, in next week, okay. So thank you for listening. Yeah, yeah, here. No, 2 plus 2 is not deal seller. 4 plus 2 is deal seller. Okay. 2 plus 2 and 4 plus 2 both are cycloaddition reaction. But 4 plus 2 cycloaddition was invented by Diels and Elder, two chemists. So that is why we call it as Diels Seller reaction. 2 plus 2 is normal cycloaddition reaction. Diels Seller mean 4 plus 2. Okay. And now you ask your question. Yeah. This is racemic synthesis. Mean we are not utilizing any enantioselective synthesis. So here both that that 1 minute. So this olefin can come from top side or below bottom side. Okay, so you will get both isomer, both trans both alpha alpha methyl you will also get, okay. So you will get 50-50 mixture, okay. Don't think by seeing this stereochemistry, don't think that this isomer is only forming. So until you are you are not utilizing, if you are utilizing any enantioselective reagents or any asymmetric catalyst, that time only you will get one isomer. But normal condition you will get both isomer, okay. So racemic you will get both, bit alpha alpha you will also get, okay. Yeah, okay. So if you don't have any further doubts, so we'll stop today, and we'll discuss next week same time. Yeah, yeah, I will upload, maybe NPTEL committee, uh, they'll share with you, okay. Yeah, next class 26, I guess. Chanda, she will took, so she will be coming with different problem sets, okay. Yeah, same topic but different sets, right. So okay, then we'll stop today. Thank you.